Hello students, Professor Nugent here. In this video we are going to talk about the expected values of the OLS estimates. In other words, we're going to see how well do beta naught hat and beta 1 hat serve as estimates of the population parameters beta naught and beta 1 in the population regression function. Given that the following assumptions hold, we're going to show that the OLS estimates are unbiased. Number one, the population model is linear in parameters. So we're assuming that the functional form is as such y equals beta naught plus beta 1 times x. Okay, so this is a linear, a function that is linear in the parameters beta naught and beta 1. Number two, we have a random sample of size n of the observations on x and y for xi and yi for observation I equals 1 through n. So we have randomly sampled. And these observations, the relationship between these two, follow the population model in equation 1. Number three, the sample outcomes on x are not all the same. Recall that if they're all the same, then we are not going to be able to identify the estimate of beta 1 hat. And number four is zero conditional mean. The expected value of u given x is equal to 0. Finally, in order to show that the OLS estimators are unbiased, we're going to make a technical simplification and treat the xi as fixed and repeated samples. And what we're doing here is analogous to random sampling in reality. The caveat is that this implies that ui and xi are independent, which is a strong assumption, stronger than the zero conditional mean assumption. This simplifies the calculations, and you will see that in just a moment. So let's prove that the OLS estimator, beta 1 hat, is an unbiased estimator of beta 1. Let's show this. Recall how we have specified. We have derived the functional form of beta 1 hat as the sum from I equals 1 to n of xi minus x bar times yi minus y bar all over the sum from I equals 1 to n of xi minus x bar squared. And we can rewrite this as the sum from I equals 1 to n of xi minus x bar times yi all over sum from I equals 1 to n of xi minus x bar squared. So this is a simplification that is the result of techniques using the summation notation. Please check it out in the appendix. Now I want to write the denominator. I'm going to just denote this as total sum of squares in x. Right, that's just the variance in the xi. And I'm going to substitute in the regression function for yi, so that this is equal to the sum from I equals 1 to n of xi minus x bar. Now substitute in the regression function. This is beta naught plus beta 1 xi plus ui. This is the population regression function. We have the population parameters and the observations on xi and the unobserved error ui. This is all over SST x, the total sum of squares of x. Now let's factor out these two terms so that we have the sum from I equals 1 to n, and we have xi minus x bar times the beta naught, plus sum from I equals 1 to n of xi minus x bar times beta 1 xi, and likewise sum from I equals 1 to n xi minus x bar ui. This is all over SSTX. Right. Now we're going to start back up at the top of the board. Now we have in this term the sum from I equals 1 to n of xi minus x bar. This is going to be 0. Right? Because if you sum the deviations from the mean up, you get 0. They average out to be 0. So this is equal to beta naught times 0. And recall that we can write the sum from I equals 1 to n of xi minus x bar times xi as the sum from I equals 1 to n of xi minus x bar squared, and that's times beta 1. And I'm going to write beta 1 in front of the summation notation because it's not part of the sum. And then we have plus the sum from I equals 1 to n xi minus x bar times ui. This is still all over SSTX. Very good. So this term drops out, right? And observe that the sum from I equals 1 to n of xi minus x bar squared, that's the total sum of squares of x. So you have beta 1 times SSTX plus sum from I equals 1 to n xi minus x bar ui. And let's write these in, break this apart, SSTX, SSTX. Alright. The SSTX cancels out here, so that we have beta 1 plus the sum from I equals 1 to n of xi minus x bar times ui all over SSTX. Great. I'm going to do one more thing, and I'm going to define this variable di as the difference xi minus x bar. So this is equal to beta 1 plus 1 over SSTX. I'm just bringing out the denominator times the sum from I equals 1 to n of di, recall that di is xi minus x bar, times ui. And this is beta 1 hat. Now I'm going to take the expected value of beta 1 hat, right? Because that's what we want to get at, the expected value of the OLS estimator, and show that the expected value of beta 1 hat is equal to beta 1. So the expected value of beta 1 hat is the expected value of this whole thing, beta 1 plus 1 over SSTX, sum from I equals 1 to n of diui. Alright. Now, the expected value of a population parameter, which is in effect a constant, is the constant in and of itself. So this is equal to beta 1 plus expected value 1 over SST x times the sum from I equals 1 to n of di du. Alright, and recall that we are treating the x as fixed in repeated samples. This is sort of like if we're looking at the relationship between wage and education, taking 3 levels of education and then sampling 3 random people with those values that have different values of wage. Okay, so we're sort of setting the xi as fixed, treating this as fixed. If SST of x is fixed, then it's not a random value, and we can pull it out of the expected value. Beta 1 plus 1 over SST of x. And we have expected value, sum from I equals 1 to n, di ui. Right? And again, the di, this is a function of x. It is not a random value, we're treating it as fixed, so we can pull it out of the expectation as 1 over SST of x times the sum from I equals 1 to n of di times the expected value of u. Alright. Now folks, what is the expected value of the u? This is 0, so this whole term goes to 0. This whole term goes to 0, and the expected value beta 1 hat is equal to beta 1. So on average, our OLS estimator is equal to the population parameter beta 1. So it is unbiased on average. Sometimes we may have a beta 1 hat that's a slope estimate that's higher than what the true slope may be. Sometimes we may have an estimate that's lower than what the true value may be, but on average, it's going to be equal. Now, if any of the assumptions fail, unbiasedness probably fails. Especially assumption number 4, the 0 conditional mean assumption. So the possibility that the error contains factors related to x is always a concern, and if it arises can result in spurious regression, where you get a relationship that is seemingly statistically significant, but in fact what you are capturing is the relationship between factors contained in u, that correlation between the factors in u and x, and how they matter for y. So we're going to get into those details a little later when we talk about multiple regression. But note that keep in mind that if any of our assumptions fail, then we probably do not have this result that the OLS estimator beta 1 hat is equal to the population value beta.